Okay, this is the last part of Chapter 14. We've got a couple lectures on this. This is part 4 in your lecture guide, and we're here discussing what is the change in pH after we add base or acid to a buffer. So we know a buffer is composed of a mixture of an acid and a base. These are both present in a buffer, and these are both weak acids and weak bases. And then if we dribble in protons from a source like a strong acid like nitric acid, protons are going to react with the basic component of the buffer, and that's going to create more acid. Okay? So there's already acid in the buffer, but the acid that is originally in your buffer is unreactive because acids don't react with H+. Now, if we have a buffer that's composed of an acid and a base, and we add hydroxide to this, the hydroxide is going to react with the acid component of our buffer, and the base will be inert and unreactive and just hangs out. Okay, so the acid will react with the OH minus to give more base. Now, it's convenient to keep track of the quantities here using an ice table, and I'll show you how to do that. Okay, so our problem here in the lecture guide on page 36 is to calculate the pH change if we add a pellet of NaOH to 500 milliliters of buffer that's composed of 0.2 molar NaHCO3 and 0.2 molar Na2CO3. Now, what I'm going to choose to do here is calculate everything in terms of moles. You could do it in terms of molarity, but you'll very, well, I'm just going to use moles, okay? First, we want to identify the substance being added, okay? So NaOH is being added. And this is a base. And bases will react with the acid. And we have two substances present. We have Na2CO3 and we have NaHCO3. The substance with more hydrogens is going to be your acid. So the NaOH will react with NaHCO3. Now, I like to leave the sodium ions off, so we'll go ahead and do that. Sodium carbonate is basically sodium ions, which we're going to ignore, and carbonate. Okay, so we'll use carbonate. Sodium bicarbonate is sodium ion, which is a neutral spectator ion, and bicarbonate, which is my acid, and I'm going to use that. So up on top of the ice table, we want to write the acid-base reaction. Okay, that's kind of step one here. So HCO3 minus is my buffer weak acid. Okay, and this is aqueous, right? And it's going to react with hydroxide ion, which is being added from, sodium hydroxide. Okay, so we don't need to worry about the Na of the NaOH. And this will give us, I'll just use a one-way arrow, this will give us the conjugate base, carbonate, and liquid water. Okay, and we just chart down here the initial change in equilibrium. So in the word problem, we have 500 milliliters of 0.2 molar And let's see, off to the side here, I'll just do green. So 500 milliliters of 0.2 molar. So 0.2 molar and 500 milliliters is equal to, got to be a little careful with the decimal places here, is 0.1 moles. Okay, the liters cancels. So I think this color is more visible. So the initial amount of bicarbonate is 0.1 moles. The initial amount of carbonate is also 0.1 moles. Okay, sure, there's lots of water present. The hydroxide that's being added is a pellet of sodium hydroxide that is 0.0015 moles. Now, we don't need to write moles everywhere, but I'm just really over-explaining this. Now, if you look at these two quantities here, the one that's less or least is going to be your limiting reactant. And that will be x. Okay, so you know how this is going to decrease by x. We actually know this is going to decrease by 0.0015. Okay, this will therefore decrease by 0.0015. Okay, and that's on the left side of the reaction arrow. And on the other side, reactants get used up, products are formed. So that's going to be your plus x, okay? And then we add the columns, right, to get the equilibrium values here. So 0.1 minus 0.0015 is 0.0985. And these two here are going to be 0. And 0.1 plus 0.0015 is your 0.1015. Okay? So we're not trying to figure out the equilibrium constant or x or anything. It's just for organization, and I recommend this, okay? Now that we have these equilibrium values here in the last row, we can now perform the pH calculation using the Henderson Hasselbach equation. Okay, so the pH is going to be equal to pKa plus log of the base concentration over acid. Okay, and remember, the acid is the one with more H's, so that's on the bottom. The one with less H's is on top. The base is on top. And we just grab those values and we plug them in here. Now, you want to refer to an appendix for the pKa of your acid. That's HCO3 minus. So make sure that guy is in the acid column. And what you see there is it's near the very bottom. The pKa of this is 10.3. Okay, so it's 10.3 plus log of 0.1015, 0.0985, and what we get here for a value is 10.3 plus 0.013, and that comes out to be 10.31. Okay, so that's the pH of the reacted substance. So do a reality check, right? The buffer to begin with, I didn't show you the math for this, but it has a pH of 10.3, and it changed to 10.31. It went up, okay? If you're adding base, it's going to become more basic, which means higher pH. And that seems to be the case there. It didn't go up much, and this nicely illustrates how buffers are resistant to pH change. So let's do another practice problem here. Okay. Let's say I have a buffer that's made from acetic acid, sodium acetate, okay, and I'm going to add .03 moles of sodium hydroxide or something like that, okay? So there are a couple things we want to do here. We're adding hydroxide, which is a base, and that's going to react with the acid. So you just leave this here for a while, okay? You don't mess around with it. If you go to Appendix 3 in your lecture guide, you'll see that acetic acid is kind of in the middle of the table. It has this formula, HC2, H3O2. And you want to write that as a reactant. You want to write that reacting with hydroxide. Doesn't matter too much about the arrow here. And then for the products, you want to write acetate. And if you look at Appendix 3 and you drag your finger over to the base column, you'll see C2, H3, O2 minus. Okay. Now, to balance this chemical equation, you need water here. It's not important for the math, and you could accidentally leave that off and be okay. Now, once again, what you do for the ice table is you plug in the moles. In this problem, I gave you moles, not molarities and volumes to work with. So under the acetic acid, we want to write 0.12. Under the OH minus, we have 0.03. Under the acetate, we have 0.18. And, we don't care about water here. This value here is the limiting reactant, so this is going to all go away. Okay, from the, reactants go away, and there's a reaction from left to right. That's why I like to use this arrow here, because we know which way this reaction is going. So minus 0.03, minus 0.03, and on the right we put plus 0.03. Okay, and then you'll want to add these, do your subtraction here. This is 0.09, this is nothing. We have 0.18 plus 0.03 is, 0.21. Okay, so first is to, write out the chemical reaction, get all this ice table. And then next is to use the Henderson Hasselbach equation. Now the pKa for acetic acid, once again, in that Appendix 3, is equal to 4.74. And we're going to expect this pH to go up from whatever its initial value is. Now in this problem, I want to do something a little different here. I want to calculate the pH of the initial buffer, and that means before reaction. before we added the hydroxide. Okay, so we want to, plug that into the these formulas are kind of crazy, but I'll just write base on top and acid on the bottom, and we get 4.74 plus log. Okay, and we want to enter in the initial values here of the the word problem that was originally given to us in this orange font. So that's the that's initial buffer before reaction. So I want to kind of see what the initial pH is. And the base, remember, is the one with less hydrogens, so it's going to be 0.18. And the substance with more hydrogens is the acid. So make sure you have those in the correct spots. And let's go ahead and do this on our calculator. And the pH for this initial buffer is 4.92. Okay. Now, if we add sodium hydroxide to this, this should go up. Okay, that's what we're expecting. So for part B here, I want to calculate the pH of the final buffer. After hydroxide ion is added. So we use the same formula. But remember, after reaction, we use these values in green that we figured out, the 0.09 and the 0.21. Remember, the guy with the fewer numbers of hydrogen is the base. That's this 0.21, and that's going to be on top of the fraction. I'm sorry. So let's plug these in. .21 and the other one was 0.9. Okay. So let's calculate what that pH is. Okay, that's 5.11. Okay. So let's do some analysis and comparison here. We're starting with a pH of 4.92, and it is indeed going up. So that's in the right direction. If we wanted to calculate the change in pH, remember that's the delta, the triangle means final minus initial always. So the final pH is 5.11. The initial pH is 4.92. Okay, and if we punch that in quickly on our calculator so we don't have to think about it, that's 0.19, okay? So that's not, this is still a buffered solution because after reaction you do have quantities of weak acid and weak base still present, so this is still a buffer, okay? This amount of hydroxide that we've added is very small and has not overwhelmed the buffer. It's still within its buffering capacity. Okay. All right. Let's do a problem here. What is the initial pH of a buffer made from 0.15 moles of HF and 0.20 moles of sodium fluoride? Okay. And what is the final pH of the buffer? maybe I should say the buffer above. After a small amount of NaOH is added, let's add 0.06 moles of sodium hydroxide. Is added, are added. Okay, so that's your question. All right, so go ahead and try and work on that, and we'll continue on to the next video.